So my name is Abhilash. I will be talking about cloud. And so this series of lectures are taken from a course that we teach over a semester, right? So I'm trying my best to fit all the content into 5 lectures, right? So it is a bit of a challenge, but hopefully I'll give you enough to get excited about cloud, right? So the idea is to show you some cool systems and some cool ideas on which cloud is built, right? So we will try to give you some breadth, right, and some depth. So the challenge is if we don't give you enough depth, then you don't appreciate it enough, right? So we'll mostly study 4 different systems in 4 lectures. And in every system, there is a cool idea that I hope you really, really appreciate and enjoy, right? And on top of it, lot of infrastructure is built, right? So with that out of the way, let us start with what is our understanding of cloud. So anyone wants to define what they think cloud is? Right. So it provides some services. It it also provides storage. It provides
compute and storage services that we can access over the internet.
provides compute. Right. Anything else? Anyone wants to add?
System
Huh? Over a network. Yes.
different system connected to a computer and you can use its services, its GPU power and data capacities.
GPU. Yeah. Right. So the idea is basically cloud is this loosely defined term, right? It's just a collection of resources that the users can interact with, right? And cloud offers a pay as you go model, right? So you don't have to pay for things that you're not using, right? And this gives us many economic advantages. So we'll first start with a bit of economic advantages, then we'll dive into technical stuff. So first thing is you don't have to manage your own resources, right? So if you own a laptop, let us say it crashes every 5 years, right? So that's roughly 1800 days. But if your system, if whatever service you have has lot of data, maybe you want to split your data across 200 laptops, 200 servers. So one laptop is crashing pretty much every 9 days, right, on an average. So this is pretty annoying. I mean, you were trying to build your Instagram or Facebook or whatever, but every 9 days, one thing or the other is crashing, right? And in real data centers, 200 is a small example. You have like tens of thousands of machines. So when you're trying to build big services, let us say you're trying to train a big ML model, one machine crashed and you have to restart your entire training process. That's pretty annoying, right? We really don't want to do that. So we don't want to manage faults. This is incredibly boring task. And as computer science engineers, we are better suited to do something else, right? So we really don't want to do this. And once something goes down, downtime is very expensive, right? So if you are a bank, you cannot say that you lost last 1000 transactions because my disk had crashed. You cannot say such things because you lose all your trust, right? So downtime is expensive in trust. It is also expensive. Let us say you are Amazon and you are doing your Prime Day sale, and you are earning millions of dollars every hour, and because your computer went down because the CPU overheated or there was a tornado in your area, there was an earthquake, there was electricity issue, right? You might be losing millions of dollars every hour, right? You really can't afford such things. So the good thing about cloud is it tries to provide you some fault tolerance, right? So instead of having a physical hardware, you try to rent a virtual hardware, and we will talk about what that is in a minute. So even if physical hardware crashes, your virtual machine is hopefully still up, right? So let us just take a look at the guarantee that AWS provides, right? So this is called a service level agreement. Every cloud provider has a similar SLA. So what they are saying is, if I rent you a machine, and if that machine was not available 5% of the time in a month, then you don't pay us anything, right? So they give you direct quote on the availability of their instance, right? So they are there to manage the individual faults that are happening, right? So CPU overheats, electricity is gone, tornado comes, hits the data center. You don't have to care, right? If AWS cannot keep up their promise, then you don't have to pay them, right? And they keep up their promise. Otherwise, they don't have a business, right? So it gives you certain fault tolerance and moves you away from managing physical resources, because that's pretty annoying, right? Then it also gives you elasticity. So let us say you start a blog or whatever, and since it is the beginning, you have 10 users and your system works well. But all of a sudden, you wrote a blog about Winter System School, and obviously you now have millions of visitors in seconds. So your poor laptop will not be able to keep up, right? So cloud also promises you certain elasticity, because they have tens of thousands of machines, right? Then cloud can also provide you proximity. So if your users are in India, in Delhi, they might be getting good service, right? But all of a sudden you write about something on your blog and you start receiving a lot of attention from Canada, you will not see good response times, right? So we can test this out. So this is going to ping every AWS data center from my local laptop. So we can see, since Ohio is on East Coast, we are getting around 250 millisecond, but California, which is on the west coast of the US, is getting 1 second, which is quite bad. Okay, better. Yeah, so Hyderabad is 200 millisecond, but the farther you go geographically, the higher ping time you will see, right? So there is also not that great. If you are trying to compete with a company based in Canada for Canadian users, you cannot compete with them sitting in India, right? Because Google has done a study to show every 100 millisecond you add in your end-to-end latency, 7% of users drop out, right? They don't want to interact with your service if your service is slow. So the benefit of cloud is, let us say you design an application, you host it in India. If you start seeing users in Canada, you can move some of your service to Canada, right? So you can play well on the proximity front as well. So why take this system school, and especially cloud? In very high likelihood, you will work with cloud, right? You will not be able to get away from it. Even if you work at a startup, if you do large companies, like you heard Mohit, both of his companies were in cloud. If you are doing ML, right, you will be training large machine learning models. There is no way you can train it on your single computer. If you are, hopefully, if you get into research, you will consider cloud, because it is a lot of fun, as we will see. So in this, we will study some real systems, right? So there are theory stuff, but we are on the second floor, so we will study systems. So cloud also has a lot of theory, but we'll focus on real systems. Okay, so when I talk about cloud, I like to talk about 3 aspects of cloud, which is, the first is virtualization, which is how do you rent a VM and what is a VM. exactly what is a VM. Then second is computation. So you have access to so many physical resources, you have access to GPUs, accelerators and whatnot. How do you use them effectively? How do you program them? And the third is storage, right? How do you manage your data when things are crashing left and right? So disks are crashing, but you don't want to lose your 1,000 transactions. But we will not be talking in a lot of detail on virtualization because we only have 5 days. So I will just introduce it a little bit now and the challenges involved with it, but mostly we'll be focusing on computation and storage. Okay, so anyone wants to define what is virtualization? Yes.
So, phenomena which abstracts away most of the things and gives you a clean slate to work upon.
Abstracts away lots of things and gives you a clean slate. Okay. Any other attempts?
Something that isn't real.
Something that isn't real. Yes. Okay. Yeah. So, I mean, we get it, right? But that's the deal about defining. So the way I defined it is act of virtualizing physical resources. But that is just so not fun. Like I used virtualizing in defining virtualization. So it is tough. It is tough to define it. So we will just look at it through an example, right? What is virtualization? So let us say you are doing an investment, right? So you buy 10 grams of gold, right? And your plan is after 20 years, this will become very valuable, lot more valuable than just cash. So after 20 years, you plan to sell it, let us say, right? So you are taking a physical resource, which is gold, and you want to keep it with yourself, and you want to sell it after 20 years. So the problem with this approach is now, let us say you have to move houses, right? So you came to Delhi, some of you have came from Karnataka. So now you have to carry this gold with you because you are not sure that your roommate will not steal it, right? So there is this management overhead. Anywhere you go, you have to take this with you, or maybe you put it in a locker of a bank, right? Then every time you take it in and out, maybe there are small scripts, so your gold is falling away, that precious money is losing because some of the gold is, you have to protect it from temperature, humidity and whatnot, right? So this is the problem with physical resources. I mean, I don't care, right? I only wanted to sell this gold, but now I have this extra overhead of managing the temperature and whatnot, right? So what people have figured out is to instead sell virtual gold, right? Which no finance people call them virtual gold, they call them gold bonds. Right? So instead of buying physical gold, the idea is you just get a certificate from Government of India that from today you own 10 gram gold, right? It's just a slip. It is virtual gold, so they are promising you that when you sell after 20 years, it will be worth as much as physical gold, but they have virtualized physical resource, right? So you don't have to manage this physical gold anymore. You can keep this virtual gold with you, and it can be, yeah.
A stupid question, maybe,
Yeah.
but if it's just a piece of paper, is it backed by actual gold?
Yes. So
They don't just issue it as slip of paper without having the gold in supply.
yeah. So that's the other issue of how much you can give, right? So if someone is just handing out golds left and right, then, and the same issue happens with cloud, right? So if you are handing out VMs left and right and you don't have enough physical machines, when someone is trying to use your VM, you better have a physical machine, right? Otherwise you will violate your SLAs. right? So same problem. So this has to be regulated, that you should have certain gold in the bank before you can hand out gold bonds. But I'm not a finance expert, so okay, so what is the benefit from the buyer point of view? The buyer has no management overhead. Hopefully, managing a piece of paper which can be scanned and later printed out is easier than managing real physical gold, right? And from the point of view of seller, so seller can now do something interesting, right? They can do over provisioning, which was not possible before, right? So let us say I have 10 kg of gold in my bank, right? This is my cool locker. So previously when I was handing out physical resources, I could only hand out 10 kg of gold because I only have 10 kg of gold. But now that I have virtual resources, and hopefully not everyone will try to sell their gold at the same time, I can hand out lot more gold, right? So I can hand out 100 kg of gold bonds, promising that anytime you come to me for 10 gram gold, I will have gold to give you, right? So this is a statistical bet over time that hopefully not everyone will come to me at the same time to get their gold, right? So I can make this statistical bet that I will over provision, right? So I will sell out lot more gold than I actually have. But of course this has to be controlled so that you can stay within your SLA. So the same thing happens in the cloud, right? So all these big companies, Amazon, Google, they already have a lot of physical resources, right? So they are running their big websites. So they already are managing lots of data centers, right? Lots of compute, memory, GPU, whatnot. So what they can do is they can hand out these VMs, right, to their customers, and they can also over provision, and they do over provision, right? So yeah, do you have a question?
How is over-provisioning possible here? Because unless it's backed by actual hardware, unlike in case of the gold, where you could bet that no one will come at the same time, here if you provision to too many customers, you don't have that much hardware.
Right. So the hope is not everyone is visiting, not everyone is getting peak traffic at all times, right? So if you are not using your VM can be stopped and put away, right? And someone else's VM will run. But we are not going deep into virtualization to study all that. But the idea is if you're not using your VM, it will be stopped and put away. And if you want to use it, let us say you try to SSH into it, it will be resumed from where it was stopped, right? So that is a
Like if the company has 10 systems and it is assigning those systems to 10 users, suppose the users are not using that much those systems and half of the time the systems are not used. Now the company assigns it to more 20 of the users, and now the past 10 users start using more the system. Now how the companies are managing this?
yeah. So this is an economic bet, right? So if 10, so this is a statistical bet, right? So if they are not able to keep up with the SLA, then they basically lose money, right? So they make the bet in a conservative way such that you can meet your SLAs at all times.
Everything is based on statistics.
Yes. So you try to study that this VM gets hot at this time and stuff like that. So it's an area in itself which we will really not discuss in this. Yeah.
This is logical in terms of computation, but what about storage? Because people will prefer this data to be safe and
Yeah. So this is multiplexing over computation and RAM, not over storage. So storage, you have to buy enough storage to keep everyone's data. You cannot say I will delete this person's data. Yeah. This is about computation and memory. Okay, so some advantages of virtualization. Let us say you have physical machines, and in those physical machines you are packing VMs, right? So again, we are not going deep into virtualization, just showing you a glimpse of what happens. So now these companies can hand out VMs to different users, right? And but this sounds pretty risky, right? What if user 2 is Uber and user 1 is Ola, and Ola sees who is booking a ride, stuff like that, right? So, but in VMs you also give isolation, right? That one VM cannot see what the other VM is doing. VMs also give snapshot and resume, right? So you can take away a VM, snapshot it, and later when the user wants to use it, you can resume it from the same point. VMs also give migration, right? And you can even do live migration. While the VM was running, you move it away to a different physical machine. So this gives you a lot of features like consolidation. So let us say I wanted to restart this physical machine, then I can slowly move away its VM to a different machine, restart this physical machine, and from VM point of view, they don't see any downtime, right? They maybe see 10 millisecond downtime, which is nothing. Then so migration also gives you load balancing. So let us say this physical machine was not being used much, and this physical machine was struggling to keep up with these 3 VMs. You can move a VM from one machine to another. Okay, so that's all we will talk about virtualization. Any questions? Yeah.
So will we be the ones who will be doing the load balancing, or will that be server?
Yeah, so the hope is it depends upon what you are trying to do, right? So if you are the cloud provider, then you have to do this management and orchestration. If you are a cloud researcher and this is the problem you are working on, then you are trying to optimize the statistics here. But in the beauty of cloud is all about abstraction, right? So it hides away all the details from you, right? So from your point of view, you just have a VM. You don't know where it is. You don't know when it got moved, right? So you just have this clean interface of VM. So if you are a ML researcher, for instance, then you don't have to worry about it, right?
What do you mean by optimization? Like in terms of
Optimization is basically you want to hand out as many VMs as you can, while keeping up the SLA, right? So the more VMs you can hand out, the more money you can earn. But if you start skipping on your SLAs, then you are losing money, right? So it's a optimization problem, which we will not talk about.
Like in creating virtual machines, there is a overhead. Like when we create virtual machines on a laptop, like it is not able to use the whole resource of the laptop. So does the like
Actually, that's not true. So VMs nowadays have very low overhead, like virtually no overhead.
Every Docker container can be assumed as a VM.
Yeah, so typically VMs, Docker containers are put inside VMs because containers give less isolation than VMs, and hopefully you will see some of that in the cybersecurity course, because in Docker container the kernel is shared, right? So if you can bypass the kernel, then things can become problematic. So in VMs give you better isolation.
When
Then
people say hyperconverged architecture, what are they really saying?
Okay. So I have a lot of material to cover. Let me just answer this. So let's keep the questions in. Yeah. So I think what Mohit meant was basically compute was being managed by different companies, storage was being managed by different companies. So I think it's not an academic term; it's an industrial term. So I'm not too familiar with it. But I think what he meant was he was putting storage and compute in the same node inside VMs. So now storage company can manage the storage VM, compute company can manage the compute VM, something like that. I don't fully know because it's not a academic term. Okay, any other questions before we move on to computation?
so does the Amazon create its own virtual like in creating virtual machine, does it use its own application, or like does it use like some
There are open source So VMs run on top of something called a VMM, virtual machine monitor, also called hypervisor. So there are some open source hypervisors like Zen, KVM, Kimu. So Amazon just released their own called Firecracker, and that is what they're using. So Firecracker borrows a lot from Kimu, and that is what they're using. So mostly it's a open source world for virtualization.
What are these hypervisors doing?
Yeah, so we really don't have time for that. But let's, so hypervisor manages the VMs, manage the isolation, that, yeah. But it's, I mean, we teach a full course on hypervisor, so, yeah.
Yeah, let's say Amazon gives out 100 VMs. Everybody requests for Ubuntu.
Ubuntu, yeah.
It's all 100 VMs. So is it everybody has a separate Ubuntu instance, or is it somewhat shared?
Separate Ubuntu instance.
So is it not a waste of
Yeah, so,
space?
so the question is, if everyone is running Ubuntu instance, are we wasting space? So in some cases, yes, but the hypervisor sitting under the VMM will try to optimize that. So it is called same page merging. So hypervisor will see that these two VMs have same OS page, so they will back it with a common physical page. But the
That could be ideal for a long period of time. So how to maximize that utilization?
yeah. Yeah, so as we can see, compressing a semester course in in 5 hours is quite tough, and it's pretty good. Like, you have all these questions, and when you work with cloud, these are some of the questions that you struggle with. But I want to introduce more questions for you to make your struggle even higher. Right, so I am sorry to not take all the questions. Hopefully we can take them offline, but let me keep checking forward into computation, right, because this is also pretty interesting topic. Yeah, but if you do have questions, feel free to reach out to me over email. Hopefully we can interact during winter system school, but I want to carefully utilize the lecture hours to cover the things that I have to cover. Okay, so now you have access to, let us say, now you have a lot of power, right? You go on AWS, you rent out VMs. So now you have access to thousands of VMs. How cool is that, right? But now we want to use them effectively, right? Otherwise, you're just paying money and not doing anything with it. So we would like to do distributed computation, where you can effectively utilize all your VMs, right? But in general, I do teach distributed computation, but my first advice is don't do distributed computation. It's like the third rule of Fight Club. So because it is very complex, right, and programming itself is already hard. So if you can avoid distributed computation, don't do distributed computation, right? So when do you really need to do distributed computation is when your data does not fit in memory, right? So you have lots and lots of data, like Google's search graph, Google's web graph, and you want to do page rank. It is not going to fit in your laptop's memory, right? So too bad, you have to do distributed stuff. So this is, actually you have to carefully think about this for your application, right? So typically we assume, oh, it is big data, we have to do distributed. It's not quite true. So if you look at the RAM sizes nowadays, if you purchase a server, you can get a server with 1 terabyte to 4 terabytes of RAM, right? So even if you have a big graph with billions of vertices, it will fit into memory, right? And when it fits into memory, it's good to try to do it on a single machine, right? Or maybe you don't have enough computational units, right? So you wanted You want some CPU, GPU, TPU, accelerator, whatever, but you don't have it, right? And you want to use a variety of them in your computation. And this is coupled with the runtime, right? So if your runtime requirements are small, but the best runtime you can get on your local CPU is not going to meet the deadline, right? So we try to make it even more parallel and run it in a distributed setup, right? So if you have these requirements, then enter the domain of distributed systems. If not, avoid it, right? Okay, but the way things are moving, it cannot be avoided, right, forever. It will come to you. Okay, so when we have computation, we are worried about a few things. So we are worried about scalability, right? So we have lots of machines and we would want to use them effectively, right? And we will define more precisely what scalability means in a moment. You also worry about fault tolerance, right? So I had a long running job that takes a day to run and it's spread over hundreds of machines, and one machine crashes, I have to restart my job, right? So I really would like some fault tolerance. Even if a machine crashes, the overall output of my job is correct, right? That is what I want. Then I also have to worry about straggler mitigation. So what tends to happen is if I have hundreds of machines, one machine maybe the temperature is high, so it is CPU is getting throttled, so it is not running at full speed, or maybe its disk has some error, so its input output is slow, right? So it's, if you have lots of machines, you have performance parity, right? So some machines are faster, some are slower. So you would like that the slower machines don't hold back your job, right? So you would want to mitigate what are called stragglers. These are the workers which are slow for whatever reason. And the traditional issues of programming still remain, right? So you would want ease of programming, right? And you would want correctness, obviously, right? So all these traditional issues that are there in programming still remain, right? But we have these new issues that we want to tackle. Okay, so any questions on this part? Yeah.
Can you elaborate on correctness part?
I mean, this is general program correctness. So let us say, given a file, count how many words are in it. You would want that whatever computation you have actually finds the words, right? So this is just correctness. So you do sorting, you get sorted output. Just regular correctness. Nothing new here. Yeah. Yeah. So like I said, so the question is how can, so first of all, you can have heterogeneous architectures, right? Because every machine in a data center will not be the same, right? They are upgraded over time. You don't suddenly buy 10,000 machines and remove all the old 10,000, right? So you have heterogeneity inside your data center that gives, makes some machines slower and some faster, relatively speaking. But even with homogeneous machines, you can have stragglers because of some issue, right? So let us say the fan has broken on a machine. So it is running, but it is, the CPU is overheating. So the OS will slow down its frequency, right? So it is not able to churn code as fast as other machines, right? But we just lump all of that into straggler, right? So some machines are slow. We don't want slow machines to affect our job completion times. Okay, so let's talk about scalability and we will spend some time on it and try to understand what is our, try to define it formally. So what is our understanding of scalability? What do you think?
So suppose we have a web app and the load on my web app increases. So
Mhm.
I should be able to back it with appropriately with enough compute so that the performance remains same. The performance doesn't decrease.
Responsiveness.
Yeah. Resource on demand. So resource on demand, responsiveness, provide enough resources to appropriately meet deadlines, right? So this is a tricky question, right? So resource on demand is a little bit different from scalability. That's called elasticity, right? So we will not worry about that. But this question is similar to what you must have seen in algorithms, right? If I ask you what is a fast program, what it ends in 1 minute, it ends in 1 second, right? So we don't have a language to talk about fast programs until you study algorithms, right? Once you study algorithms, then you have this beautiful notion of O of n. You can say O of n is faster than O of n log n, right? So we would want to do the same treatment to scalability, right? To define it analytically, so we can compare two different computations, which one is more scalable than others, right? So we are going to define it analytically, but the problem is defining analytically is pretty hard, right? Real hardware, if you look at hardware, hardware is so messy, right? Cache time is so much fast, like the time it takes to hit the cache is so much faster than time it takes to hit the RAM. That is so much faster than time it takes to hit the network, right? Then integer operations are much faster than floating point operations. Then you can also have frequency modulations, right? So OS is doing this DVFS to slow down CPUs, speed up CPUs, right? So this really doing analytical understanding of systems is extremely hard, right? Because there's just so much going on in the hardware that it's just very hard to model. So we will take lead from the algorithms folks, right? So what they have done is they just build a simplified model of computation, right? They just say that basic operations take constant time, right? So if you are trying to do a plus, if you are trying to do a multiply, if you are trying to do a equality, all of this takes constant time, whether it is integer, floating point, whatever. But we know in hardware this is not the case, right? So we are just trying to move away from the hardware slowly because we want to simplify our analytical model of computation, right? So we can happily say O n log n, stuff like that. Then we also assume memory access is free, right? So there is no cost to moving stuff in and out of memory, right? So we assume hitting DRAM is same as hitting the cache, right? We don't worry about locality of an algorithm generally when we say its time complexity, right? So these are the assumptions made by a single computer, right? And based on that, we define our algorithms time complexity. But parallel hardware is even messier, right? So in parallel hardware, you also have network topology, right? Which computer is connected to what computer? How are they connected? Are they over Ethernet? Are they over Wi-Fi? What is the packet loss rate, right? Are there retransmissions? So if we try to do all this is pretty messy, right? So we don't want to do all this. And there are stragglers and load balancers and all this, right? So we don't want to do all this. We are building a simplified analytical model so we can compare two algorithms without getting into this messiness of real world.
The assumption is compute is on one node while data is distributed across nodes as well.
No, so in distributed systems, computation and data are both on multiple nodes.
It needs to be aggregated to give one out.
Depends on what you are trying to do. Right? If you are trying to compute a sum, then it has to be aggregated. If you are trying to multiply every number by 2, let us say, then there is no need for aggregation.
You still have to concatenate.
yeah, so again, depends on what you're trying to do, right? Okay, so we don't want to get into this messy hardware, so we will just add a new thing. We'll just say that communication, because this is a new thing that we typically don't have to deal with in algorithms, is constant time, right? So we will additionally add up the time for communication, right? Because communication is expensive. But again, I want that we keep this in mind, that this is a oversimplification, right? So this, what we are really saying is, let us say I have two threads. These threads are talking to each other, right? And they are on the same CPU. Then this what time this takes is the same as these two threads which are running on two different data centers, right? So I am really oversimplifying the model of computation by saying that threads on the same CPU, if they talk to each other, take the same time as the threads talking to each other across data centers, which is really not true. So we should take theory with a grain of salt, right? But it's still useful. It lets us do analytical reasoning to talk about O and log n and stuff like that, right? So it's really, really useful. Otherwise, we don't even have a language to talk about scalability. Okay, so let's look at our first parallel algorithm, right? So the algorithm is adding n numbers, right? So let us say we have n workers or processors or threads, whatever you want to call them, and each of them bootstraps with holding one number, right? And the goal is we want to add all the n numbers. So what is the best serial time for this, for adding n numbers? Huh? O of n? Anyone else? Oh. Huh? Log n. Log n is not possible. I mean, you have to look at a number at least once. You can't do in log n. Right? No, serial time. Okay, so let's just look at a simple parallel algorithm. So let us say this worker, what happened? This worker sends its number to its neighbor in the first round, right? Then its neighbor adds it up. So we end up with 4 numbers. Then in second round, we end up with 2 numbers, right? So there is a very simple parallel algorithm, right? So what is the, let us see what is the runtime of this algorithm. So what is the computation, what is the height of this tree? Log n. So the computation cost is basically log n, right? Because it cannot be more than the height of this tree, because at every level we are doing only a single basic operation, add. And the communication cost is also amortized in this. So the overall parallel time is log n, right? So is this a good algorithm? So we brought down n to log n. That sounds pretty awesome, right? So if we look at speedup, speedup is defined as how much faster your algorithm now runs. So it becomes n over log n, right? Is this great? It sounds pretty great. If you had 1 million numbers, then you are doing computation in million over something like 6 or 30. If this is log base 2, so million over 30, right? So we received a lot of speed up. Correct. So, but the problem is we used 1,000,000 processors to get this speed up, right? So, what is the ideal speed up? What is the best possible speed up you can ever get using n processors? Huh?
Order of
One? N, right? So if a task takes certain time, if I am putting n workers to do the same task, if they are able to do it in 1 by n of that time, then that's the perfect parallel algorithm, right? So
Can you please define speed up again?
speed up is Ts over Tp.
Can you please define TS and TP?
Ts is the best possible serial time
Okay.
on one worker, and Tp is your parallel time. Okay, so n over log n is much okay, so n over log n is less than n. So this means processors are not efficiently utilized, right? So if we look at the execution of this algorithm, right? So this is the timeline. Let us say we were adding 4 numbers on 4 processors, right? So when the algorithm starts, P4 sends its number to P3, P2 sends its number to P1, right? Then P1 does an add operation, and this is just sitting idle. This is just sitting idle. P3 is doing an add operation. Then once this add completes, then P3 will send its number to P1. Then P1 will do an add operation, and P3 will sit idle, right? So we can see that a lot of the processors are, so the actual useful work that we could do was only this, right? The rest was overhead added due to parallelizing this algorithm, right? So either processors are sitting idle, or they are waiting for some data or sending some data, right? So ideally we want that in our computation that processors don't sit idle and they have least amount of synchronization as much as possible, right? So you work on your own data as much as you can. Okay, so we define another metric called efficiency. This is how well are you using your processors, right? So this is defined as speed up over number of processors, right? So this is basically saying how well, if efficiency is 1, then everyone is doing useful computation at all times, right? So efficiency is between 0 and 1 always, because the best possible speed up you can get is P, which is the number of processors. So the best efficiency you can get is between 0 and 1. So efficiency of our algorithm is 1 over log n, right? Because we had n over log n as our speed up and n as the number of processors. So our efficiency of that algorithm is 1 over log n. And as we can see, if you increase the number of, as you increase n, efficiency hits 0, right? So your processors are sitting idle, most of your processors are sitting idle most of the time, right? So you're not efficiently using your processors. Okay, any questions so far? Yeah, so that is a different question. So here we are just looking at a simplified land where we have one parallel computation. We have asked for P processors, and we are looking at how long it took to complete the computation. But you are right, when you have the OS will actually give this idle to someone else, right? So processor is actually not sitting idle, right? So, but we are only looking at in a algorithmic perspective. Okay, any questions? This part? So E efficiency is defined as speedup divided by number of processors. The number of processors we had was equal to number of numbers we were trying to add. So the number of processors we had was n. This is our P. And S was n over log n. S was n over log n, right? Good. Okay, so let's try a different algorithm. Here we will not have n processors. Let us say we only have p processors, right? And we have split n by p numbers to one processor, right? So we have p processors. Every processor starts with n by p numbers. So our algorithm is the same. We first do this addition locally, then we send this number over. We end up with two numbers, then we send these two numbers, and we end up with the sum. Okay, so what is the height of this tree? Log p. Right, so it depends on how many processors you have. It doesn't depend on how many numbers you had, right? Okay, so the computation time is now n by p because I was doing this addition initially, right? Plus this in these this guy has to do log p additions, and communication cost is also log p, right? So overall TP is theta n by p plus log p. So now we can compute our speedup. Speedup is n over n by p plus log p. This becomes 1 over 1 plus p log p over n, right? Sorry, p over. And then efficiency becomes 1 over 1 plus p log p over n. Okay, so we can try to plot this.
So before we move forward,
Yeah.
just go back to previous slide. So here, just clarifying, P is 4 in the example you have shown and N is 60.
Okay, so E is 1 over 1 plus p log p divided by n. Okay, let's try to plot this. So efficiency can go up to 1, and we are increasing the number of processors. So let us say I'm keeping n as constant, and I just increase number of processors. So I have to add only 16 numbers, but I keep throwing processors at that algorithm. So how will E look like? If P is infinity, what is the value of E? 0, right? So roughly it will follow some curve, right? So if you keep throwing processors at it while keeping the work same, then your efficiency will drop, right? Because the processors will start sitting idle no matter what algorithm you have. For fixed n or fixed TS, if I keep throwing processors at it, the processors will start sitting idle, right? So efficiency will go down. And what if we do the opposite? I keep the processors constant, and I keep increasing the number of numbers that we are trying to add. Increases, right? Right. So in this case, it will eventually actually hit 1, right, when n tends to infinity. So this is a general characteristic of every parallel system, right? So if you keep the work constant and keep throwing processors at it, the efficiency will go down, right? And if you keep the processors constant and keep increasing the problem size, hopefully the efficiency goes up. But actually this is not true always. So in some cases, efficiency will remain poor, right? So those are unscalable algorithms. Okay, so finally we are ready to define our scalability, which we started with. So the definition of, so we have to define yet another term, final term called W, which is called isoefficiency. So W is the rate at which n needs to grow when I add a new processor. So if I give you a new processor and I tell you that efficiency needs to remain constant, what is the rate at which n needs to grow? So in this case, n needs to grow at p log p. Right. So if n and p log p are growing at the same rate, then the efficiency remains constant. Right. So typically we use this isoefficiency function to compare two different algorithms, which one is more scalable than the other. Okay, so question, is a lower W better or a higher W better? So let us say I have two algorithms, one the isoefficiency is p log p and another algorithm isoefficiency is p. Which lower is better? Why is lower better?
It will increase our efficiency.
cope up with the speed.
Huh?
We will need less processor to cope up with the same speed.
If you want to go from one to the other, it will be easy.
Right. So lower is better, right? So in the worst case, if W was exponential of p, that means just for efficiently using one more processor, I have to, let us say, use lot more data, then that algorithm is not as scalable, right? Okay, so we will right. So overall, the takeaway is basically anytime you take an algorithm from serial to parallel, it adds all this overhead of communication and idling, right? Either your processors are sitting idle, they don't have work to do, or they are doing too much talk with each other, and that could have been better spent on doing the actual computation. So generally the goal is that we increase the actual computation work and reduce the idling and communication. Okay, so this is, but so far we haven't, this is all comes in under the umbrella of parallel algorithms, right? So we have not yet touched the distributed aspects around fault tolerance and all that. So, but we will stop here. So any questions? Okay, thanks everyone.